Now, what is the best model? Till now, according to our understanding, the model with highest accuracy and the least error is the best model. The model that uses maximum information available in the given data is the best model, or the model that has minimum squared error. If it is regression case, the predictions need to be as near as possible to the actual values, or the model that captures all the hidden patterns in the data is the actual very good model, or the model produces best prediction results is the best model. Imagine that we have multiple models, model 1, 2, 3 on the same data, using different techniques. How to choose the best model? Now we need to be a little careful here. The error on the training data is not a good measure of performance on the future data. What do we mean by future data? The unknown data. Model is built on a certain data set, given data set. A good model, we are always measuring its goodness of fit on the given data set. Now that might not be a good measure all the time. What do we exactly mean by that? So the data set that we use for model building is the training data set, and the till now we have been looking at training error only. We need to actually look at some other error also called test error or holdout sample error. What exactly is test error? What is test data set? What is test error? What is holdout data set? What is holdout error? So what exactly is the most accurate model, and how do we see it? What is the different measure that we also need to consider apart from the training error? So let us look at an example of the most accurate model and where exactly it fails in satisfying the condition of test error. Let us try to fit the best model on fiber bits data. So we just want to predict the active customers based on remaining variables. So let's start with a simple model, or the first default model that we are trying to fit, and then see its accuracy. So the accuracy of this particular first model is around 84%. Now let me relax the condition of CP obviously and the minimum split. Now let me see the new accuracy. On the same data set, I just change the control options and let me see what is the accuracy of the second model. I'm building a different model. Now the accuracy of the second model is 95%. So earlier I built a model where I got an accuracy of 84%. I played around with some of the parameters, I got an accuracy of 95%. Now is this 95% the final accuracy of our model? Is it true representative of the model prediction power? That is the question that we need to ask ourselves. Maybe if I change the parameters a bit more, change them minimum split and complexity parameter, definitely I'll get much more accuracy. So what exactly really defines the accuracy of the model? So this is called a training data set, where the model that is built upon the data, that is the input data that is used to build the model, is called training data set. Now we are looking at the training error. Is training error the true or the final indicator of the overall model accuracy? That is the question that we need to ask ourselves. Is 95% accurate model, is this the best model that I can produce? In reality, there are two different type of data sets and two different type of errors when we look at it from a model building point of view. So till now, whatever data we used, the input data for building the model is called the training data set, and the error that we have been calculating is the training error. So we have an accuracy for the best model that is 95%, and we have an error of 5%. Now is that model really good? Yeah, on the face of it, it looks really good model. Okay, now error on the training data is known as training error. The low error rate on the training data definitely might not always mean the model is good. We need to be careful in the training error. A good accuracy on training data might not always result into a really or indicative of a really good model. What really matters is how is the model going to perform on the unknown data set or the test data set or the new data set that is going to come out. We need to find out a way to get an idea on the error rate on the unknown data set or the test data set. One easy way is to just keep a part of the data set, do not use it in building the model. So remaining part, let's say I take 80% of the data and use it as training, and rest of the 20% of the data I don't touch it, though I knew the result, but still I build the model on 80% of the data and then find the accuracy on rest of the 20% of the data. Let me call it as holdout data or training test data. Then if the model is still doing good on that unknown data or the out of time data or the validation data, if it is still as accurate as training data, then we can believe the true predictive power of the model. So there are two types of data sets and two types of errors. One is training data set, that is the actual model input data. Test data set is the unknown data set or the validation data set that we keep aside to test our model. Once we build the model on the training data, we test it on the test data set to get the, it gives the final accuracy of the model or final model that is built on the training data set. Okay, generally we might not have all these two data sets at the beginning of any problem. Okay, sometimes we may have only training data set, sometimes we may have just the test data set. No, that is wrong. Sometimes, I mean all the time we will have only training data set, or sometimes we'll have training plus test data set. So what we can do is, when we have only training data set available, we can take 90-10%. So out of overall data, we can take 90% of the data as training data, keep rest remaining 10% of the data as validation data set. Validation is nothing but the substitute to test data set, or it's a temporary test data set. So since we don't have the test data set, we have created the validation data set. Sometimes it is created with the rule of 70-30, 70% training, 30% validation, or even 80-20, 80% training, 20% validation. So we create the validation data set, and then once we have the training data set and validation data set, we build the best model on the training data set, see its accuracy, call it as training error, look at the error on the test data set, call it the training test error. So there are two types of errors, like the way there are two types of data set, there are two types of errors. Training error, so the error that we have been calculating till now, the error on the training data set, it is also known as in time error. The error on the input data, the error on the known data, or the error on the data set that is used for building the model, okay, can be reduced. It can be reduced while building the model. In fact, this is what we have been trying while building the model. We have been trying to reduce the error as much as possible. We have been trying many iterations in building the model to reduce the error or the training error, okay, the test error. In fact, this is the error that really matters. So it is also known as out of time error. So out of time data error, the error on the unknown data set or the new data set. In fact, if a model is really doing good on training data set, it should do good on test data set. If it is not doing good, then that is not a really best model. It need to be rebuilt or recalibrated, okay. Generally a good model should do good both on test and training data. So we build the model on training, so with training error should be less, and we validate it on test data, test error should be less. Both of them should be as close to 0 as plausible. So if a model is very good on training data and it is not doing good on test data, that is called the problem of overfitting. Let us see what exactly is the problem of overfitting.